So here we have a slide 1, day 10. Just wanted to illustrate this. When we go through the lecture, I'll have a screen capture, but I wanted to illustrate this particular molecule with a model to help you all out with that. So if you have a bond line structure here, and you want to make a model to help you see the chair conformation and verify what that actually looks like three-dimensionally for the structure, this is the way I would do that. So notice I have cyclohexane, so that means I'm going to try to make a chair. And I've got the solid wedge here connecting the chlorine and the dashed wedge here connecting the methyl group. So that means if I imagine my ring in the plane of the paper or screen, and I imagine it flat, the chlorine would be coming out at me and the methyl group would be pointing away. So I want to make a model that shows that. So I have a model here. Notice that it's flat. I made my 6-membered ring flat. I have the chlorine here pointing out at you, just like it was pointing out of the screen on the top carbon. And on the neighboring carbon, the methyl group's pointing away from you, right? You can see this hydrogen right here is pointing out at you. The methyl group's pointing away. So this one has a solid wedge, is pointing toward you. The methyl group has a dash wedge, is pointing out at you. So that's my flat structure though, and I know this is not going to be stable. I'm just starting with this to make sure I can see the chlorine pointing up and the methyl group pointing down, matching the solid wedge and the dashed wedge. The flat structure we know is unstable because we've got torsional strain all the way around, right? Every pair of these hydrogens on adjacent carbons is eclipsing, and now the hydrogen's eclipsing with the chlorine. That's happening all the way around the top. All these adjacent atoms on adjacent carbons eclipsing. There's no staggering. That repulsion between those groups makes it very unstable. And we also know within the 6-membered ring, the bond angle is being 120 if it's flat. Push the electrons outside the ring too close together, and that causes angle strain. That also makes it unstable. So I want this to be a chair. So to make my chair, what we said in the other video was we'll take every other hydrogen on top, grab those, every other atom on the other side, grab those, and just kind of pull them together gently until the molecule's relaxed. Now I have a chair. I know I have a chair because I can see on the top of the ring each of my axial hydrogens all pointing straight up, and on the bottom my axial hydrogens all pointing straight down. I notice that the chlorine here in green and the methyl group on the adjacent carbon are both in equatorial positions. That's nice and stable. Right? There's nothing really out here to, no electron cloud out here to bump into the methyl group's electron cloud and create repulsion. And so this is the optimal rotational conformation for this particular molecule. Right? And so that particular molecule is this one here. My methyl group and my chlorine are both in equatorial positions, pointing kind of out, slightly up and down, but out from the ring rather than straight up and down. If they're pointing straight up and down, those will be axial positions, and those are much less stable. It's hard to see in the drawing of the chair conformation how the axial positions are less stable than the equatorial positions, but that's what we want to use the model for. So back to the model. Let's try to illustrate that. So I've got this particular chair. It looks nice and stable. The chlorine and the methyl group are both in equatorial positions, pointing out into space. They're not bumping into anything, creating repulsion. So if I want to rotate this to see the other chair conformation, I'm not simply flipping it over like a pancake. Doing that doesn't change the fact that my chlorine and methyl groups are in equatorial positions and quite stable. So to do a chair flip, which is what's called, it's not flipping it over like a pancake, we're just doing a flip of the single bonds, right? So when I have my chair, I've got the base of the chair, the head of the chair, and the feet of the chair. I'm going to take the head and push it down. It gives me a temporary boat with the flagpole interactions, very unstable. So then I'm going to take what was the feet of the chair and push that up to become the new head. And then if I need to, I can grab my 3 atoms on top and 3 on the bottom to kind of make sure that they're all pointing straight up and straight down. So now any chair flip changes a group that was in the equatorial position now into an axial position, and vice versa. So the chlorine was sticking out from the ring into, and its larger electron cloud was more stable out there. Now, chlorine has 3 layers of electrons, so it's a pretty big electron cloud. Being on top of the ring, it's going to start to cause repulsion with the other axial groups, right? We talked about the 1,3 axial, 1,3 diaxial repulsion, and so the chlorine repelling the hydrogens up there is unstable. If we look at the bottom of the ring, or if I flip it over, either way, I also have the methyl group in an axial position. It was equatorial, I did the chair flip, now it's axial. So I didn't have to disconnect and reconnect any bonds. All I did was rotate around the carbon-carbon bonds that exist. So this molecule is the same as the other one where they're both in equatorial positions. It's just a rotated conformation of that structure. And what I see here is the methyl group and its big electron clouds getting close to these hydrogens, causing repulsions. So any diaxial groups or 2 axial groups repelling makes it much less stable. So if this molecule existed and it rotated into this form, these repulsions would immediately cause it to rotate out of that form, push the head down, push the feet up, and now my groups are again in equatorial positions, and it makes it much more stable. So like 99.999% of the molecules would exist in this form, and when they rotate the other form, they would just quickly rotate back because of how unstable it is in comparison.